share my screen right away. This is class that we had before, and we talked about radian meters, okay? We recall what radians are, how to convert radians to degrees, right? How radians are related to this length of the arc that is separated by the radius. Okay, no worries, Hala. No worries. Thank you for letting me know. So, also we did a little practice by converting degrees to radians and vice versa. And we solved a pretty interesting example with Ferris wheel, where we have calculated the angular velocity using conversion and formula for angular velocity as change of an angle with respect to change in time. And in second class, we're going to talk about trigonometric ratios and special angles, because this is another crucial aspect of solving trigonometric functions, because we're going to use it in order to perform equivalent conversions in our functions. For example, cosine and sine functions are deeply related to each other. I believe you got a chance to get familiar with those in your previous course. So is everything clearly visible, guys? Can you give me your feedback? And we're gonna take a look into special triangles. I believe you covered this in past courses. Can anybody describe special triangles? In particular, there are two general cases where we have equally sided, we have equally sided right angle triangle, and we also have a right angle triangle with a certain ratio between angles, right? In right angle triangle, we remember that one angle is always 90 degree, and the two others, let's call this alpha and beta angles, angle alpha plus angle beta always equals to 90 degree. Based on this relationship, we can remember following special triangles. One of them where angle alpha equals angle beta, and both of them are equal to 45 degrees. And then another one where they're different exactly by 30 degrees. Basically, we have 90-degree angle is the base of this right angle triangle. Then we have, let's say, angle alpha equals 30 degrees, and angle beta equals 60. What's so special about these triangles? First of all, for equal-sided right angle triangle, we're gonna have two sides that are same length. And also, for special triangles, we prefer to choose one side equal to 1 in order to show in the simplest way. Because for trigonometric functions, when you imagine these special triangles, it doesn't really matter what length of a side they have, but rather than what ratio between side to side. For example, here you can see that two sides equal to 1, and third side, which is hypotenuse, equals to square root of 2. For another special triangle, we have side that is opposed to 30-degree angle that is half the length of the hypotenuse. This is how you could remember these two triangles. One of them has two equal sides, and 45-degree angles, and the other one has a catet of a length. If you denote this catet as B, A, and C for hypotenuse, catet A would be equal to C divided by 2. And why do we use these special angles triangles? Because they are convenient for us to show primary trigonometric ratios, sine, cosine, and tangent. Let's move on to the next slide. It is also important to understand standard position angles when we talk about them on a coordinate axis, x, y, right? Please take a look at this diagram where angle theta is set to go from x-axis to the terminal arm of this angle. Please take a moment to look at the screen. So yeah, looking into this standard position angles, first property that they have their vertex at the origin, right? Or they start at the origin, basically. Terminal arm starts from the origin, and that's basically the turning point of this angle. Initial arm lies along the x-axis. As you can see, this is the starting line, x-axis, and this is terminal arm. I'm gonna mark terminal arm as red color. And remember that you always start counting angle in positive direction from x-axis towards the terminal arm. Please write it down. Positive angle of rotation counterclockwise from right to left. Like if you imagine mechanical watch, counterclockwise. That's a positive direction for angle. Please note these 3 properties down. Okay, guys, I hope I give you enough time to note it down. Now let's take a look at the basic trigonometric ratios. I cannot be sure that everybody remembers them from past courses, so let's talk through them again. When we see sine theta, cosine theta, tangent theta, that's when we look into ratio between sides of right angled triangle. Now you see why we're so interested in right angled triangles, because when you construct an angle on the coordinate axis, you can always build a right angled triangle between the starting arm of an angle, which is x-axis, and the terminal arm, by drawing a vertical line that joins the end of the terminal arm with the x-axis. Now you got a 90-degree angle. And now this little angle theta is a part of a right angle triangle. And in this right angle triangle, we're looking into ratio between sides. For example, sine theta is a relationship between the opposing side of this angle to the hypotenuse. So for sine theta, in this particular example, you can see that opposite side to angle theta is y, which means sine theta would be y divided by r. R is a hypotenuse in this triangle. Remember, hypotenuse is the longest side, and it lays against 90-degree angle. Then for cosine, it's a ratio of the adjacent side with respect to the hypotenuse. So we're going to have x over r. And finally, tangent. Tangent is a ratio of the opposing side with respect to the adjacent one. So tangent theta would be y divided by x. Is there any questions here, guys? Mo, Safa, anybody? Any questions about basic trigonometric functions? Or basic trigonometric ratios, basically. Okay, great. And now, let's take a look at the special angles in radians. Do you remember from the past class how to convert 30 degrees to radians, 60 degrees to radians? 30 degrees to radians would be 30 degrees times pi over 180 degrees. Same for 45 degrees. It's going to be 45 degrees times pi over 180. And remember, when expressing in radians, we don't want to get rid of pi and convert it into constant number. We keep it as a letter pi, and it just tells us that it's a constant value. Can anybody give me answers for these three angles? Mo, what about you? Can you calculate it? 30 degrees to radians. Mo, can you hear me? You can use your annotation tool in order to convert and leave your comment on the desk. Can you do that? For your convenience, I'm gonna join X and Y in purple and denoting that it's tangent. And with blue, I'm gonna join R and X and say that it's for cosine. And with yellow, I will join R and Y and denote that it's for sine. Okay, so maybe this way it will be easier for you to remember. Sine, cosine, and tangent. And the way I remember it, sine, opposing side, cosine, adjacent side, and tangent, opposing over adjacent. Mo, can you hear me? Are you with us? What is 0.52? You shouldn't convert pi into 3.14. You keep pi as a constant value. For example, 60 degrees converted to radians would be as follows. 60 and 180 degrees. We need to simplify it. First of all, we can simplify it by 10, and then 6 and 18. 6 remaining would be 1, and 18, we would have a result of division as 3. So basically, 1 times pi over 3 gives us pi over 3 radians. That's for 60 degrees angle. 60 degrees angle equals to pi over 3. You can also remember that if you look at the coordinate axis and you make a circle, here at 90 degrees is going to be pi over 2, and 180 degrees is going to be pi. This angle equals to pi radians. Then here would be pi, 3 pi over, oh no, sorry, it would be 3 pi over 2. And here it would be 2 pi. So full rotation 360 degrees equals to 2 pi. Is it clear, Mo? So for the rest of the angles, for example, 30-degree angle, we can simplify again, and we're going to get 6. So pi over 6 is 30-degree angle in radians. 45-degree, so 180 divided by 45 would give us 4. So pi over 4 is 45 degrees. Basically 45-degree angle. Here is pi over 4. And you can see how these numbers are nicely positioned on this circle, right? We have 4 quarters, pi over 2 pi, 3 pi over 2, 2 pi. It also starts in 0, right? And makes whole rotation to 2 pi. Pi over 4 is in between 0 and pi over 2. Makes sense. And it's also 45-degree angle. Good. We refreshed the memory from the last class. Mo, is that clear? How do you convert angles to radians? Perfect. Do you need a moment to copy down sine, cosine, and tangent ratios along with this sketch of right angle triangle? Or you got it? Everybody, Safa, you need more time to copy it down?
No, I'm good.
Okay. And then moving on, we're going to determine the exact values for the sine, cosine, and tangents of the following radians. Keep in mind that when we work with right angle triangle, we have these special triangles that we are familiar with. So let's memorize for those triangles that have 45-degree, two sides equal to 1, and the hypotenuse equals to square root of 2. For those triangles when one corner is 30 and the other one is 60, two cathets would be 1 and square root of 3, and hypotenuse equals to 2. And 1 would be laying against a 30-degree angle. Remembering that, let's move to this part. And let's determine the exact value for the sine, cosine, and tangent of the following radians. The way I would like to do it is to convert this to degrees and then set it in correspondence with our right angle triangles. 1 and square root of 2. And the other one would be 1 square root of 3 and 2. This side is 60 degrees. This one is 30 degrees. Both are 90 degree, and here is 45 degree. Both are same. So let's take a look at P over 6. We just did it, and theoretically we can remember it, but let's convert it to degrees one more time so you can memorize it better. So pi over 6, how do we convert it to degrees? Pi over 6 times 180 over pi, right? To convert to radians, pi is on top and 180 on the bottom. If you do it inverse, you flip it. So pi is getting simplified. 180 divided by 6, 180 divided by 6 would give us 30. So it's a 30-degree angle, pi over 6. Pi over 3, same thing, we're gonna do multiplication by 180 over pi, and we're gonna simplify pi. The 180 divided by 3 is gonna give us 60 degrees. And pi over 4, if you don't mind, I would skip expanding it completely because I remember that pi over 4 is 45 degrees. Just as we showed in the previous page, where is the circle? First you split it in 4 quarters like this. We know this is 0, this is pi over 2, and then in between those, pi over 4, right? This segment, this arc divided by 2 basically. So pi over 2 divided by 2 give us pi over 4. So, and that's a 45-degree angle. But now, we need to determine the exact value for the sine, cosine, and tangent of the following angles. So let's start with sine of 30 degrees. And remember, sine of 30 degrees is the ratio between the opposing side to the hypotenuse. If we know angle is 30 degrees, we remember this is 30, 60, 90 special triangle. Side that lays against of 30 is 1, hypotenuse is 2, so the sine would be equal to 1 over 2. Great? Then cosine of 30 degrees would be adjacent side over hypotenuse, and that's going to be square root of 3 over 2. Perfect. And finally, tangent. Tangent of 30 degrees is the opposing side over adjacent. So it's 1 over square root of 3. Here's 3 values for sine, cosine, and tangent of a 30-degree angle. You can, of course, complete solving it with a calculator, but I would suggest to leave your answer as a fraction. Then for B, let me use another color. Why not use green? So sine of 60 degrees. We refer to the same right angle triangle, right? 30, 60, 90. So sine of 60 degrees would be opposing side against the adjacent one, or opposing side over hypotenuse, so it's going to be square root of 3 over 2. Then cosine is adjacent over hypotenuse, which is 1 over 2. And finally, tangent would be opposing side over adjacent, or square root of 3 over 1. And what can we notice right away? Looking into these two, sine, cosine, and these two, sine, cosine. First of all, I can notice that sine of 30 degrees equals to cosine of 60 degrees. And cosine of 30 degrees equals to sine of 60 degrees. Because they refer to the ratio between the same sides and exactly in the same way, but because we're talking about opposing angles, they give us same ratio. For cosine of 30 degrees, square root of 3 is the adjacent one, and for sine of 60 degrees, square root of 3 is the opposing one, right? Opposing and adjacent. That's why it turns out this way. For tangent, you can see that that's basically tangent of 30 degrees is an inverse of tangent of 60 degrees. Again, because they refer to opposite sides. And basically, tangent gives you ratio between these two sides. But tangent of this angle gives you opposing over adjacent one. And tangent of this angle gives you also opposing over adjacent one. I hope it's clear. And let's finally take a look at pi over 4. I'm going to clear some space for me. Moving on to pi over 4, sine of 45 degrees would be opposing side over hypotenuses. And take a look, in this case, it doesn't matter which angle we look at because they're equal and sides are equal. So sine of 45 degrees would be 1 over square root of 2. Cosine 45 degrees would be 1 over square root of 2. And tangent of 45 degrees would be equal to 1. Because ratio between 1 to 1 is 1. Please take a moment to copy this down into your textbooks, and you can even write them in the column, like first sine of 30 degrees, then cosine of 30 degrees, then tangent of 30 degrees, and write those values in columns so to better memorize them. But I would even suggest you to write them in the following way. Sine of 30 degrees, then sine of 45 degrees, then sine of 60 degrees. That way you're going to see the dependence in a better way. 1 over 2, square root of 3 over 2. Oh no, sine of 45 degrees is 1 over square root of 2. 1 over square root of 2. And sine of 60 degrees is square root of 3 over 2. Okay, let me know once you finish copying down this all basic trigonometric ratios. Guys, please work with me. So as you can see, I'm gonna use the red color for two cosine and sine that are equal. No, I'm gonna do it this way. This and this are equal. And I'm gonna use blue for sine that is equal. Sine and this cosine are equal. In the middle, basically, they both are equal. Let's use like this.
Oh, mister, it's very hard to see the tangent, like it's cut off. I can't see the rest of the numbers.
You can see tangent up on top because I wrote down tangents here as well. You see 45 degree, 60 degree, and 30 degree. I just made it as an example of how I suggest to write it down in columns. In your textbook, you can do it more organized way, but here's tangent of 30 degrees is 1 over square root of 3. And you should be able to come up with these ratios on your own by knowing the special triangles. They're on your screen, and I strongly recommend you don't just remember these ratios, remember the ap- approach how we find them. Remember about opposing and adjacent side ratios. The tangent is the ratio between the opposing and adjacent side, while cosine is the ratio between adjacent and hypotenuses, and finally sine is the ratio between the opposing side and hypotenuses respectively. How is it going, guys? I would also recommend you to note down the special triangles next to basic trigonometric functions for your convenience, because next time you look at it, you see where it came right away, where it came from. And that's, as for me, the best way to memorize it. In my school time, I always had a cheat sheet where I had right angle triangles, special triangles, as well as basic trigonometric ratios. Please let me know in the chat once you're done, okay? And then we're gonna look at one more slide and have a little break. Okay, thank you guys. Thank you for letting me know. Moving on to the next one. Let's take a look. Quadrant angles. Angles that are multiples of 90 and have a terminal arm which lies on either the x-axis or y-axis. That we briefly already touched in the previous slide when I was giving you an example of how to allocate angles using the circle, unit circle. Remember, unit circle has a length of arm equals to 1. And basically multiples of 90 gonna be 0, then 90 degrees, 180, 270, and 360 finally, and so on. If you go another 90 degrees, you will have an angle that is equivalent to 450. Is that correct? 360 plus 90 is 450 degrees. But sine and cosine of such angle gonna be equivalent to sine and cosine of 90 degrees, because basically you made one full rotation and returned back to 90. That's what we're going to discuss later. Sine and cosine are periodic functions. You may have seen how they express sine and cosine as a wave, right? So after making a full rotation, like this, between these 2 points, it's 2 pi, or equivalent to 360 degrees. We return back to the starting point. So, and when talking about multiples, in terms of radians, multiples of 90, we know that 90 degrees is going to be pi over 2. Basically, 90 degrees is equivalent to pi over 2. So every next multiple of 90 would be simply the previous one plus pi over 2. So 180 is equivalent to pi, then 270 is equivalent to 3 pi over 2, right? That's how much is pi plus pi over 2. 1.25, or 1.5, basically. Then 360 is 2 pi. Moving on, 450 would be equivalent to 5 pi over 2. And again, as soon as we made another full rotation of 2 pi, we can substitute 2 pi from here. It would get that it's equivalent to pi over 2 in terms of sine and cosine functions. Is there questions about it? Or is that clear, guys? Let me write them here for you in columns. So we're going to have 90, 180, 270, and 360. And on the opposite side, we're going to have an equivalence in radians. Here we're going to have pi over 2. 180 is going to be pi. 270 is going to be 3 pi over 2. And 360 would be 2 pi. Please note this down and let's have a 10 minutes break. How about it? Write it down as you can see it on the screen. One column is degrees, the other one is radians, and also make sure to represent the unit circle because that's your visual support in order to memorize these ratios. This is very important. I'm telling you guys, you memorize it once and it's going to be useful for you once you keep working with trigonometric functions. We're gonna have 10 minutes break at 17:55 and see you back at 18:05. 5 after 6 p.m. Okay, guys, I'm back. How's everyone doing? I hope you copied this down already. And I can see that Sapphire is still missing. And let's wait a couple more minutes for her so she doesn't miss any useful material.
Sorry, sir, I didn't leave yet, but you can
Okay.
continue with the lesson.
Okay, thank you. To take a look at the screen, now we're gonna find the exact value of each ratio using the radians. So here you can see a new ratio that you haven't seen before is second of 2 pi, and second of 2 pi is another one basic trigonometric ratio. Second is basically a ratio of the hypotenuse C with respect to adjacent side of an angle. Basically, second of 2 pi is equivalent to 1 over cosine 2 pi. While cosine of 2 pi, right? It's a ratio between adjacent side A and hypotenuse C. But 1 over this ratio would give us C over A. Hypotenuse over adjacent side. Okay? Then moving on to sine. Let's start with question A. With ratio A. Okay. I'm gonna use classic pen. Let's use some green color. So sine pi over 2. I suggest we use the unit circle now. Remember that this equals to 1. And position of angles is as follows. Pi over 2, pi, 3, pi over 2, and finally 2 pi. So sine pi over 2 would be a sine of an angle, choose the red one, that has a starting arm here and terminal arm here. 90-degree angle. Is that correct? And we need to find the sine of such angle. And how do we do that? Using the unit circle. Remember that we need to sketch a vertical arm from the end of the terminal arm to the x-axis. And in this particular case, when angle equals to 90 degrees, basically it will be parallel and equal to the terminal arm itself. And also, what I want you to remember, that basically y-axis in this case represents the sine values, and x-axis represents the cosine values. So for example, cosine of 0 degrees would be equal to 1, because you see it, arm lays along the x-axis and it has a length of 1. But when we're talking about sine of 90 degrees, it will also be equal to 1, because this time this arm lays along this axis, x-axis equals 0 and y-axis equals to 1. Or basically, sine is the ratio of the opposing side with respect to the hypotenuse. So in this case, opposing side of 90 degrees, well, basically equals to the hypotenuse, right? So as soon as they're equal, sine of 90 degrees equals to 1, because, for example, C divided by A divided by C, or if it's opposing, it's B divided by C, but we know that B is equal to C in this case, so it equals to 1. So sine of pi over 2 equals sine of 90 degrees and equals to 1. Another way to see it is whenever you have any angle, let's say 45 degree, most easiest way, 45 degree, and we have its projection on the x-axis of this, we have projection of this terminal arm on the x-axis, and we also have projection on the y-axis, right? And you can see that projection on either of these axes would be equal. So thus the sine and cosine of 45 degree angle is equal. Basically, cosine of 45 degrees equals to the length of the projection on the x-axis, and sine of 45 degrees equals to the length of the projection on the y-axis. Okay? Here would be our projections. I'm trying to clean it a little bit. Okay. Now moving on to sine of pi. What can we tell about sine of pi? Sine of pi is the sine of an angle that has a 180 degrees, right? Because this is where pi on the unit circle, and this is obviously half of the full rotation, which gives us 180 degrees. Also, what we can tell about it? We also can tell the projection of this terminal arm. This is start of the coordinate axis, and this is our terminal arm, like a arm of the watches. Projection of this arm onto y-axis will be equal to 0, right? Because it projects it to the beginning of coordinate axis. Y equals 0 in this position. Considering that, I can tell that the sine of pi equals 0. Remember, it works because we were using a unit circle, In unit circle, radius of such circle equals to 1. Also, this brings us to a conclusion. If we can use unit circle with cosine and sine ratios in order to identify them, cosine x always less or equals to 1. Okay, it's always less than 1, but greater or equals to -1. Same stuff for sine x. It's going to be enclosed in the same range. You may ask me how sine or cosine could be negative. It depends on the direction of rotation. If x is negative, for example, we rotate counterclockwise, cosine and sine will be negative as well, but not all the time. Sine and cosine would be also negative in certain quadrants. This is what we're going to get to in a bit. Cosine 3 pi over 2. 3 pi over 2 is 270 degrees, which is here. Cosine 3 pi over 2 would be projection of it onto the x-axis. And we can see that clearly this line is vertical. So its projection on the horizontal axis would be equal to 0. So cosine of 3 pi over 2 equals 0. And I'll tell you even more. Cosine of pi over 2 equals 0. So 90 degrees and 270 degrees equals 0 for cosine. For sine, pi and sine of 0 equals 0, as well as sine of 2 pi, because 0 and 2 pi are basically same point, equals 0 as well. Sine pi over 2 equals 1, and sine of 3 pi over 2 equals 1. Oh, sorry. Actually, 3 pi over 2 would be equal to -1. This is the case. So here, 3 pi over 2, we remember upwards is positive direction, and downwards is negative direction. So sine of 3 pi over 2 would be -1. When you talk about secant of 2 pi, remember that secant is inverse of cosine, basically. And secant of 2 pi would be equal to cosine of 2 pi, and cosine of 2 pi equals to 1. Right? Because this is going to be I'm going to use the pink color. It's not really visible. Let's use the green one. Cosine of 2 pi would have terminal arm laying here, and projection of this arm on horizontal axis, which is responsible for cosine, equals to 1. So it's going to be 1 over 1 or equals to 1. And finally, tangent. What can we tell about tangent of 7 pi over 2? First of all, let's identify which angle is that 7 pi over 2. 7 pi, if we know this is 2 pi, or in other words, 4 pi over 2, then plus pi over 2, we get to this point again, is going to be 5 pi over 2. Here we have 5 pi over 2. Then walking again, we're going to have 6 pi over 2. And walking again, we're going to get 7 pi over 2, finally, right? But we could have done it easier by simplifying it, by getting rid of repetitive circles, right? Because 7 pi over 2 is greater than 2 pi. It's greater than 4 pi over 2. So basically 7 pi over 2, let me clear the board a little bit. On the right hand side, I'll write it. Pi 7 pi over 2 is equivalent to 7 pi over 2 minus 2 pi, because we're substituting, we're simplifying by the whole rotation that we did. We don't want to count it twice because it brings us to the same spot. So minus 2 pi, or here I would say equal, 2 equivalent 7 pi over 2, 7 pi over 2 subtract 4 pi over 2 would give us 3 pi over 2. And that's exactly what we know, that 270 degrees equals to 3 pi over 2. And what's the value of tangent at this point? If we look here, we can see tangent, basically, we can also treat it as the ratio of sine of 7 pi over 2 over the cosine of 7 pi over 2. Because basically, if you convert it, you're going to see that it gives you opposing side over hypotenuse divided by adjacent side over hypotenuse. Hypotenuse will simplify itself, and as a result, you're gonna get the b over a. Opposing, oh sorry, you're gonna get a over b. Ratio, and that's exactly what tangent is about. So tangent of 7 pi over 2. Let's take a look into sine value here. Sine 7 pi over 2. Sine is a projection of this terminal arm onto the y-axis, and it's going to be -1. And cosine of 7 pi over 2 equals 0, right? Because this arm projected on the horizontal axis equals 0. Isn't that correct? So knowing that, we can state that tangent of 7 pi over 2 would be equal to -1 over 0. And we should remember from rational functions what type of discontinuity it gives for function. It gives basically a vertical asymptote, right? So tangent function would gonna have a vertical asymptote when x equals 7 pi over 2. Remember, sine, cosine, tangent, these all are functions. They give you a ratio between two values, right? And at this point, when our angle is 270 degrees, tangent would give us basically negative infinity. The end behavior of the tangent at around 7 pi over 2 is going to be negative infinity. Is that clear? Oh. Basically, you could say that it's undefined, but when we analyze function, it gives you end behavior of negative infinity.
I think you're muted.
Oh, that's unfortunate. Thank you for letting me know. So what I was showing you right here, right before this, I showed you the tangent function, and you can see that it has the vertical asymptote after with certain periodic recurrence. As we just showed before in our slides, at 3 pi over 2, the function would have vertical asymptote, and it will also travel to positive infinity and to negative infinity from one of two sides. I just want to make sure, have you heard what I was explaining on this drawing here? When we talked about tangent of 7 pi over 2, have you heard me then? I'm not sure for how long been unmuted.
You were only unmuted when you were Googling the pictures.
Oh, so right before Googling them, you heard me, right?
I mean, muted, sorry. When you started searching on Google, you were muted.
Okay. Did I got muted or I've been muted up until that moment?
When you searched for the graph of a tangent function, you were muted by accident.
Okay. Thank you for letting me know. So yeah, one more thing about sine function, that it has a period of 2 pi. So it means that the value for sine function would repeat itself with a period of 2 pi. And remember, at 0, sine equals 0. So when x equals 0, sine also equals 0. It means function passes through coordinate axis like this. It's 0, 0. For cosine function, it's different. It's going to be offset with respect to sine function. And when sine function reaches a maximum or 1, cosine would be equal to 0. So basically, function would look like this. Yes. And you can see that cosine function, cosine x, is a red one, and sine is a green one. When sine function equals 0, cosine equals to 1. And sine equals to 0. And also you can see that there is a turning point, basically, after which cosine and sine turn into negative values, right? And let's talk about it briefly. Basically, if you take a look at the unit circle, you're gonna sorry. So here's our unit circle. If you look at it, you gotta remember the cast rule. And we're gonna talk about. I believe you're already looked into it in the previous courses, but let me remind it to you. Basically, cast rule stands for cosine, all, sine, and tangent. CAST. So basically, how do I position cast in the 4 quadrants? Quadrant number 1, quadrant number 2, quadrant number 3, in quadrant number 4. How do we position CAST in these 4 quadrants? C would be quadrant number 4. A would be the quadrant number 1. S would be quadrant number 2. And T would be quadrant number 3. Cast. And how exactly is it useful? When we have C, so fourth quadrant, what happens is cosine theta is positive, sine theta is negative, as well as tangent theta is negative. For A, from cast, which is first quadrant, for A, all, that's why it's A, all positive. C, because cosine is positive. The rest of them are negative. A, because all are positive. Guess what happens in S? In S, only sine theta is positive. Okay? And finally, last one is T. Guess what? In T, which is third quadrant, only tangent is positive. The rest of them are sine and cosine are negative. Please note down this cast rule. And let's look into related acute angle. I'm going to sketch another coordinate axis here. And looking into related acute angle is going to be such an angle that is the smallest angle between the terminal arm and the x-axis. For example, if our terminal arm is in first quadrant, then this would be our acute angle. If our terminal arm, which is going to be green now, lays in second quadrant, and like we have this big angle, which is greater than 90 degrees, then the acute angle would be the one from left side, the one from the side that is closer. So basically, if green wants some angle alpha, we would have 180 minus alpha equals to acute angle, let's call it beta. Beta would be acute angle. In case if arm lays in second quadrant. In third quadrant, what happens that if we go in farther, let me use orange this time. So we go somewhere here, the related acute angle would be an angle that is again closer to the x-axis, going backwards basically. So if this theta is our main angle, let's call it theta in first example 2. If our theta is greater than 180 degrees, then basically what we get that the acute angle beta would be equal to theta minus 180 if theta is greater than 180. If theta is less than 180 but greater than 90, 180 minus theta. So we subtract the if 180 is greater than the angle, we subtract from 180. If 180 is less than the angle, we subtract from the angle. And finally, fourth quadrant. And what you think, if the angle is greater than 270, acute angle would be the one that reaches the x-axis faster and would be basically continuing of it. And in this scenario number 4, if theta greater than 270, what we're gonna do is we're going to subtract 360 minus 270, or sorry, minus theta. We don't have exact value, but from 270 to 306 minus theta equals beta, right? This remaining piece for a full rotation. Please take a moment to note this down, okay? This is very important to remember about acute angles because, again, whenever you work with sine and cosine, for example, your sine of a principal angle would be equivalent to cosine of acute angle. Because sine of this is projection here. Oh, no, sorry, it's an equivalence, basically. Yeah, projection here. And cosine would be projection here. Oh, no. Yeah, so basically, acute angle and principal angle could be set in equivalence when calculating certain sine or cosine values. Basically, if you have, let's say, just a second. Yeah, for example, if you have in the second quadrant, and you have angle that is, let's say, 120 degrees, and you would like to find the sine of 120 degrees, how would you do that? You say that sine of 120 degrees is equivalent to sine of 180 minus 120. And you can check it with your calculator or wherever you like, but you're gonna see that sine of 120 degrees is equivalent to sine of 60 degrees. That's why we need to know how to work with related acute angle. And moving on to example number 3, now I would like you guys to participate a little bit. You see here you ask to find the exact value of each ratio, and I can see there is more of us now, and we have exactly 6 questions here. So we can assign each question for each one of you. So let's say Ahmad gets A, Hala, yeah, in an order, Hala gets B, Mo gets C, D gets Muhammad, just M because the more convenient, and Safa, let's go with E. We'll keep cotangens outside for now. I'll remind for Hala that cosecant, CSC, is the reciprocal of sine function. So basically, CSC of x equals to 1 over sine x. Please use your annotation tools to sketch on the board. Can you show your solution, Hala? You say that sine of 330 equals negative 1 over 2. So using the cast rule, sine would be positive in first and second quadrant, but 330 degrees is in fourth quadrant. Yeah, so it's going to be negative. And sine of 330 degrees is equivalent to sine of 60 degrees, isn't it? Oh, no, of 30 degrees, yeah. Equivalent to sine of 30 degrees, but in negative side, so it's going to be negative 1 over 2. So your answer is negative 2. That's correct. Let me show it here. So basically what Safa did, she got an angle of 330 degrees. And her acute angle beta equals to 30 degrees. And she remembers the CAST rule, which means that sine function is positive only in first, in second quadrant. So here it's negative. So negative and 30 degree for sine is 1 over 2. So we're going to get 1 over negative 1 over 2 equals negative 2. No worries, Hala, I wrote it down for you. Basically, here is one more step that we have to show that sine of 330 degrees equals to sine with minus of 30 degrees, right? And sine of 30 degrees equals to 1 over 2. Negative based on the cast rule and 30 degrees based on the acute angle. Let's see what Safa showed us here. Okay, let's give a moment for the rest of the students to finish their part. Ahmad, Mo, and Mohammed. Good job, Hala. Good job, Safa. Let me see your solution, Safa. 11 pi over 6. Or square root of 3 over 2. Okay, well, how would I do it? First, I would show that 11 pi over 6 is actually less than 2 pi, right? It's 1 and something. So basically, it's going to be somewhere. Let me use the blue color as it's for Hala, or for Safa, sorry. So it's going to be somewhere here, almost full rotation. 11 divided by 6. This would be 11 pi over 6. So 11 pi over 6, we should convert it. Oh, basically, we can find this angle in radians using the acute angle, right? So it's going to be 2 pi minus 11 pi over 6, which gives us 12 pi over 6 minus 11 pi over 6, and gives us pi over 6. And pi over 6 is equivalent to 30 degrees, if I remember right. Pi over 6 equivalent to 30 degrees, and also cosine function is positive in fourth quadrant based on the cos rule, right? So it's going to be basically equivalent of cosine of 30 degrees, and cosine of 30 degrees is, as we know from special triangles, cosine of 30 degrees would be square root of 3 over 2. Great job, Safa, no questions. But I wish next time you could show the same explanation as I just did it. Because if you write something like this on the test, it would be confusing unless it says you can use a digital calculator. For mole, let's see, mole, you say you got 1. Tangent of 225, let me see. So 225 degrees is exactly in the third quadrant, and tangent is positive in this quadrant. And let's see, let's use an acute angle for tangent in this scenario. If it's 225, and you need to find, so it's somewhere here, we need to find beta that is closer to the x-axis or the acute angle. So basically, sorry for that. It's gonna be $200 angle would be equivalent to 270 minus 225 degrees, right? For acute angle beta equals to 45. Isn't that correct? And as we know, for 45 degrees, tangent of 45 degrees equals to 1. Do you see more how we get this? So tangent of 45 degrees equals to 1. We can also show it from the special angle triangle where two angles equal to 45 degrees. These two sides are 1, and tangent would give us relationship between 1 over 1. And that gives us 1, basically, right? For Muhammad, let me help you, Muhammad. Good job, Mo, you got the right answer. And what about Muhammad? Sine of 5 pi over 4. 5 pi over 4, if we look on the unit circle, 5 pi over 4. We know that this is pi, but 5 pi over 4 is greater than pi and less than 3 pi over 2. Because 3 pi over 2 could be also written as 6 pi over 4. If we multiply by 2 numerator and denominator, and 6 pi over 4 is greater than 5 pi over 4. So it's going to be in the third quadrant. In third quadrant, you should remember the cast rule, right? C-A-S-T. In third quadrant, only tangent is positive, It means sine value would be negative in this case. And let's also find the acute angle beta, for which we would have to substitute from 6 pi over 4, which is 3 pi over 2, substitute 5 pi over 4 to see that acute angle would be pi over 4, or pi over 4 is also known to us as how much? Exactly, 45 degrees. But remember that because sine is negative in this quadrant, basically sine of 5 pi over 4 is equivalent to negative sine of 45 degrees. And sine of 45 degrees is 1 over square root of 2, but minus, we're going to put it in front of the fraction. So this answer for D is going to be negative 1 over square root of 2. Mohammed, is that clear? How did I do this? I hope so. If you have any questions, guys, please free to ask them now. This is the right moment, because this is something you better understand and be ready to do your homework based on this. And then we'll move on to real problems when we're gonna work with functions and subtract and add sine and cosine values. And here, I want you to get familiar with how to evaluate them. Good job, guys. Every one of you gets a star today. Everyone did a great job. Except I didn't receive the response from Ahmad. Ahmad, are you with us? Okay, seems like not. Moving on to final slide. Please, I want you to take a look at this problem, and the first one of you who can figure it out and explain his solution properly would get an additional mark. Example 4. I'm gonna help you with the sketching the drawing. So the point P, -5 and -12, is one of the terminal arm of theta in standard position. Here is the circle. Here the coordinate axis, x and y. We don't actually need a circle, we just need x and y. Y-axis, x-axis, and x point P is -5 and -12. P, and it lays on the terminal arm of angle theta. So basically, our terminal arm passes through this point. This our angle theta in standard position, as it says here, right? Question A, find the 3 primary trigonometric ratios for theta. So sine theta, cosine theta, and tangent theta. Remember that all of these are ratios between the sides of a right angle triangle, A, B, and C, right? There's 3 sides. And sine, cosine, and tangents are ratios of these 3 sides. And question B, find theta in degrees to the nearest degree and in radians to the nearest hundredth. So here you see, in radians, you need to find it to the nearest hundredth. So you can actually substitute pi equals 3.14 to solve this one. In previous question, there was no need to substitute for pi. So please, guys, first one to give me a right answer. You have 3 minutes. If no, this is going to be part of your home assignment. If somebody can finish in 3 minutes, it would be great. Is it clear, guys? No worries, I won't deduct marks for wrong answer, but I will give marks for right answer. So sine theta basically gonna be the ratio of the opposing side to the hypotenuse. Opposing side in this case. Well, let me fix the marking. So this is C hypotenuse, this is A, and this is B. Opposing side would be A, and hypotenuse is C. So we're gonna have sine equals A over C. A equals 12, right? It's projection. Look, it's projection on the y-axis. So A equal to the length in the y-axis. So A equals -12. But what about C? How do we find the hypotenuses? And that's where you need to remember the Pythagorean theorem. C would be equal to square root of A squared plus B squared. So basically, it's going to be 25 plus 144, square root of it is going to be 169, square root of it, and 169, I believe it's square root of 169, it should be 13. So hypotenuse is equals to 13. Let me check it. Yeah. This example number 4, please note it down. This is going to be part of your homework. I'm going to also post it to Google Classroom along with another problems because you haven't solved it in class, but you see it's just a good example for practicing. I already showed you how to find the sine of this theta angle. Please find cosine, tangent, and finally express angle theta in degrees and radians. Okay? I hope you enjoyed today's class, guys.